Welcome back to Integrated Science. I'm Miss Sparks, and today we're going to make the connection between the two energy sources that we have been describing the past couple of days with our kinetic energy and our potential energy. And so, what we're going to be looking at is how can we take quantitatively information from kinetic and potential, and how can we take qualitative information and describe the motion and talk about how the energy is being transferred. So the law of conservation, there's several different ones that we will talk about throughout the year. This is probably the epic, most highest point of this class because the law of conservation of energy will be brought into play for each of the other units that we will go through. We'll talk about how energy is transferred in space, how energy is transferred in magnets and wave energy. We'll talk about how energy is transferred through conduction, convection, and radiation, and then how that even applies to the Earth. So there's several different ways in which we are going to look at it. So the law of conservation of energy states just itself that energy cannot be created or destroyed. It only converts from one form to another. So let's kind of break that down on what that actually means. So it's stating that energy is always potentially there, and when a force is applied, then it can move into kinetic energy and it converts from one to another, from a one to another. So an object, let's say that you are standing on a diving board and you are standing there and you're not moving. You're just kind of like, okay, I'm about to jump. So if you think about that, you have potential energy on that diving board. You have a height, you have a mass, and you have gravity pushing down on you. Then when you jump, your potential energy converts to kinetic energy. As you fall towards the water, you gain more kinetic energy because now your mass is also being associated with your speed. And then when you hit the water, it slows back down. So it's converting back and forth. So when we talk about the law of conservation of energy, what we're trying to describe is that kinetic and potential energy are always both there. So once again, the energy is not created or destroyed. It's just transferred back and forth, back and forth. Nothing is changing from one product to the next. And that's what this is kind of saying here. The law means that energy is a product that cannot be produced from nothing or disappeared from nothing, meaning that energy is always present. It just needs a nudge to get it moving. So think about even, let's talk about like a firework. Let's say that it's 4th of July and you have a sparkler in your hand. It has the potential to take off and start letting out its sparks. However, you need to provide that kickstart for it. And so it's always there, and when the sparkler is moving, it's got kinetic energy as it's releasing the sparks into the atmosphere, and then from there it will die off, but the energy is still not gone. It's just moved somewhere else. It's moved to the atmosphere as a form of heat. So we'll kind of make this connection as we move forward, is that there's always like a chain of events that are happening, and that is very much so in the case with the law of conservation of energy, is that there's always being a movement with it. So there is a formula that we'll talk about with this, and it's called total mechanical energy. And pretty much what it means is how much energy in the system is dedicated to potential energy and how much energy in the system is dedicated to kinetic energy. And so total mechanical energy is the amount of mechanical energy is merely the sum of potential and kinetic energy. So let's break that down. The sum means adding in algebra or in arithmetic. So we are going to be adding the kinetic and potential energy. And we always want it to balance out to whatever the original amount is. And so that sounds kind of weird. Like, what is she talking about? So let's take a look at our skier right here. So we can see that he's on an alpine slope and he's moving down and across this little course. So we have the ability to find how much energy he has at each one of the systems. To find the total, and that's always going to change depending on the first position, their original position. So in this case, that's going to be right here. Here's his starting point at the top of the hill. So once we find his potential energy, that's going to be the total energy moving through the system. And as you can see, they gave us the height here. They didn't give us his mass, but we could go back and find it. But if we take a look at the numbers they've provided, we've got kinetic energy at 0 joules, and that should make sense. He's sitting at the top of the hill, he's not moving at all, where potential energy is 50,000 joules, and so that's our total energy in the whole system. So if we go through to each one of these different spots, we can also figure out what is his total energy. So if we add 20,000 kinetic energy to 30,000 potential energy, that is going to equal up to 50,000, which is once again that original amount that we have found there. Same thing if we go down here and look at his position here, they've given us the kinetic energy of 35, the potential energy of 15, add them together. Once again, we get that magical 50,000. And so this one is that we're looking at the total energy always being 50,000. And even if we look here at the end, we can see that transfer. So at kinetic energy, he had 0 up here because he was sitting. But if you think down here at the bottom, he should be 100% booking it, moving super fast because he's at the bottom. He's gained all this energy moving through the slope. And we can see that transfer. At the bottom of the slope, he has 50,000 joules of kinetic energy and 0 potential energy. So still, if I were to plug them into this formula, 0 plus 50,000, I get that total 50,000 once again. It's just that it's moved, it's transferred. So once again, the law of conservation of energy says energy is not created or destroyed. It's there. We can see it at each one of the spots. His total energy of 50,000 is at each one of the spots. It just transfers back and forth, back and forth. So we can see he has little kinetic energy here. He's gaining kinetic energy here. He's got a whole bunch of kinetic energy here. And then it kind of transfers a little bit back to potential because his height goes up so high. And then at a whole bunch of kinetic energy down here. So we're able to use this to help us find a whole bunch of other pieces of information. So I might say, hey, how much mass does this skier weigh? Well, we can figure that out too because we do have enough information to plug it back into our potential energy equation and just work it backwards. So 50,000 would be our potential energy, and we have the height of 100 meters. We know he's on Earth, so that's 9.8. So we could go back and figure out his total potential energy as well, or sorry, his mass as well. And then that could help us figure out some other pieces of information too. So, and that's where we're going to spend a little bit of time is how can we use these pieces of quantitative information to kind of help us figure out everything. So one of the most famous scientists of all times, Mr. Einstein, came up with this little equation, E equals mc squared. And so this equation actually helps us understand total mechanical energy. So Einstein was 100% way brilliant and above his time in being able to understand things that they didn't even have the tools and technology to help explain. But he was able to say that energy can be converted to matter or mass, and mass can be converted to energy without all the technology that we have today. So let me read this to you and then we'll kind of talk about this. So Albert Einstein worked on many things throughout his career, and energy is among the top in his investigations. Einstein found that the amount of energy an object can possess is proportional to its mass, meaning that if you have energy moving at such a fast rate and it is connected with the constant of light, it can convert into mass. And then mass can release energy. It's easier to think about it the opposite way. Mass and light can create energy. Think our sun. The sun is a great example. It is a massive gas ball in our solar system, and it is producing light, and that is due to the process of fusion, which we'll talk about later this year. But there is a whole bunch of energy that is being released from the sun. So we can also have that in the opposite direction, is that if you have energy moving at a super fast rate, it can create particles too, particles of matter. And so that is kind of hard to think about, like how this energy just appears out of nowhere. And this equation helps us kind of figure out maybe where the beginning parts of our universe began, because during that moment of energy that was released, there was enough energy that then started to create our small subatomic particles, protons, neutrons, and electrons. And then that created everything else that we can see today. So there is proof behind this. We have particle accelerators that have been able to demonstrate how energy can create matter in small amounts. It creates some of the particles that string theory produces, and we'll talk about this a lot when we get to the space unit. The last thing I just want to kind of touch on is that here on Earth, things we want, especially machines, we want them to be efficient, meaning that we want them to be able to produce the most amount of work with not using a lot of energy. So I feel like cars are a great example of this. If you think back several years, even if you're like someone that maybe is in a family that likes older cars, the fuel efficiency of cars have become really great to this point. And now we even have cars that can run on electricity. So it's completely changed. So they've become what we call more efficient. And it just means that the quality, usually expressed as a percent, that measures the ratio of useful work output and work input, meaning that you put gas in your car and you expect your car to run. At this point in the game, we hope to put enough gas in our cars that it should last for a long period of time versus a shorter period of time. And so that's what we call efficiency. And we will talk a little bit about this and how we can look at things, machines being 100% efficient versus maybe only 65% efficient, depending on how much energy is put through the system. So hopefully this was helpful, and we will look qualitatively and quantitatively at both of them as we move further. Thanks.